Okay, turn over to the review problems, please. Okay. Those definitions you need to know for your test. Be able to define radioactivity or radioactive decay as the breaking down of a atom's nucleus, an unstable nucleus of an atom. That's what radioactive decay is. And it's spontaneously breaking down. A physical constant is a quantity that doesn't change. Ground state is going to the lowest energy state of a particle, and spectroscopy is identifying chemicals by the light they either emit or absorb. Either way. Number 2, what is the mass of the average calcium atom in grams? So you would look at your chart, and your chart for calcium tells you that it is 40.08 AMUs. You want to know how many grams that is, so you're going to go 1 AMU, and they tell you there what the grams are. It is 1.66 times 10 to the negative 24th grams. So you're going to do this. That has 4 significant figures. That has 3. So your answer has to be in 3 significant figures. So it gives you 6.65 times 10 to the negative 23rd grams. Okay? Great. The next one, it says a specific isotope of nitrogen has a mass, and it gives you the mass. What is the mass in AMUs? What would the symbol be? So first, you're going to take the mass that you're given, which is 2.49 times 10 to the negative 23rd, and that is grams. And we want to convert this to AMUs, and we know that 1.66 times 10 to the negative 24th grams is 1 AMU. Did I get that right? Yep, okay. Equals three significant figures both places, so that's going to give us 15 AMUs. So we would write this isotope as nitrogen 15. Okay. And make sure you answer all the questions he asks, because he'll ask more than one in some of these, like that one. We look at the magnesium 25 atom, and you want to know how many protons, neutrons, and electrons. You look on your chart. Its atomic number is 12. Therefore, it has 12 protons, 12 electrons. And then you have 25 minus 12, which is 13 neutrons. Everybody's okay with that, right? Okay. It's probably
on number 3, I wrote 1.50 times 10 to the first. Is that okay?
Yes, that's fine. But then did you write it as nitrogen 15?
I did not write it as nitrogen.
Then you would miss half on the test. Make sure that you finish, okay? Okay. Let's see. An atom has 5 protons, 5 neutrons, and 5 electrons. What is its symbol? It is boron, so it's B, and it's got 10 particles between the protons and neutrons, so it is boron 10, B with the little 10 to the upper left, okay? What is the most abundant isotope of phosphorus? And phosphorus is P, and if you find it on your chart, its mass underneath it, underneath the P, is 30.97, which is almost 31, isn't it? So P31 would be the, phosphorus 31 would be the most abundant isotope of that. What is the most difficult thing to do when it comes to making a nuclear bomb? Getting the isotope enriched. In other words, getting enough of the fuel to do the bomb. So isotopic enrichment. Number 8, what do nuclear power plants use to keep a chain reaction from getting out of control? That would be the control rods. Number 9 lists the colors of light in order of wavelength from longest to smallest. That would be Roy G. Biv. That's what they're looking for there. Number 10, light has a wavelength of 231 nanometers. What is its wavelength in meters? So we have 231 nanometers. We want to know what it is in meters. So we're going to go like this. Nanometers on the bottom, meters on the top. 1, 10 to the 9th equals. And that's going to end up giving you 2.31 times 10 to the negative 7 meters. Yes. Okay? Okay. Let's see. Then we go to number 11. What is the frequency of light in the previous problem? All right, so now we have the wavelength. Frequency, remember, equals c over lambda. C is 3.00 times 10 to the 8th meters per second over 2.31 times 10 to the negative 7th meters. And so we have 3 significant figures both places. So that's going to end up giving us 2.31 times 10 to the negative, am I in the right place? No. 1.3 times 10 to the 15th. 1.30 times 10 to the 15th hertz. Good. Everybody okay on that so far? Okay. All right, let's see. Number 12, light has a frequency of that. What is its wavelength? And so here, we want to find the wavelength. So wavelength equals c over the frequency. This is 3.00 times 10 to the 8th meters per second divided by the frequency that was given, which is 3.45 times 10 to the 17th hertz, which is per second. 3 significant figures at both places. It's going to end up giving you 8.70 times 10 to the negative 10th. And you're going to be left with meters because the seconds will cancel. Okay. Number 13, to what does the term electromagnetic waves refer? That is all the light that comes, all the light energy that comes from the sun. Number 14, Number 13, to what does, we already said that, including invisible light. Number 14, name 3 categories of electromagnetic light other than the visible light. You need to know all those for your test. Just, be familiar with them. You don't have to name them all, okay? Be familiar. Number 15, a photon has a frequency and it gives the frequency. What is its energy? Well, if you're going from frequency to energy, you're just going to use this, aren't you? Right? And it asks here, it gives you the frequency as 1.94 times 10 to the 16th hertz. So you just plug in Planck's constant, which is given, plug in your frequency and multiply. It's that straightforward. Number 16, a photon has the energy of that. What is its frequency? Once again, you're just going from here. If you have the energy and you want the frequency, you're just going to solve. And you're just going to work it that way. So you're just going to plug in. It's not a big deal. Number 17, now we're given the wavelength and we want to know the energy. And that's one more step. So let's do that one. We know that frequency equals c over lambda. Here we're given the wavelength, but we want to know the energy. Once again, the energy, we need to get to the frequency to be able to get to the energy. And so here we are given the wavelength. And we know that the speed of light is 3.00 times 10 to the 8th meters per second. So the wavelength has to be in meters. So this is going to be 6.12 times 10 to the negative 7th meters. And you do the math, but that's what it's going to come out at. Okay? And so that's going to end up giving us 4.90 times 10 to the 14th. And that's hertz, but that's this, isn't it? And then if we plug that into this, and you just multiply that number to Planck's constant, that's going to give you a number in joules, and that will be the energy of that photon. The next problem works the same way. You're just going in the other direction. You're going from energy back to wavelength. Is everybody okay with those? Yeah. Okay, turn the page, please. It says the electron of a hydrogen atom is in the N5 orbit. To get back to its ground state, it releases a single photon with a wavelength of 95 nanometers. If the electron of another hydrogen atom is at ground state, what wavelength of light must it absorb to get to N5? It's going to be 95 nanometers. It takes 95 to get up to be the excited state, and it takes 95 that it'll release to get back to the ground state, okay? Number 20, the electron of one hydrogen atom moves from N3 orbital directly to the ground state. The electron in another hydrogen atom moves from N2 to the ground state. Which electron released a photon with the longer wavelength? Longer would be lower energy, wouldn't it? So which one would release the one with the longer wavelength? N2. And then which one released a photon with the higher frequency? That would be N3, because it would have to go farther, higher energy. 21, what is the key assumption in the Bohr model of the atom? And that is that electrons are restricted to a specific orbital. They can't exist in between, or excuse me, they can't be found in between. How's that? Okay, fill in the blank. Atoms are more than 99% empty space. Very good. Consider the emission spectra below. If the mixture of the two elements are as follows, what elements are they? And so if you work these out, it's hydrogen and lithium.